Hi there viewers, we are Team Promethium, and for today's tutorial video, we will discuss about the topic of spectroscopic method of analysis. To better understand the spectroscopic methods, this CRTV will include the following topics. First is the atomic absorption and emission spectroscopy and their quantitative applications. Second is UV-Vis and IR spectroscopy instrumentation. And lastly, spectroscopy based on molecular photoluminescence and scattering. So first, what is spectroscopy? Spectroscopy is an advanced analytical technique focusing on the absorption, emission, and scattering of electromagnetic radiation by atoms and molecules, allowing qualitative and quantitative information about the interaction of matter with electromagnetic radiation. When radiation meets matter, the radiation is either absorbed, emitted, or scattered. Atomic spectroscopy was the first application of spectroscopy developed, and it can be split into atomic absorption and emission spectroscopy. Atomic absorption spectroscopy, in short AAS. Atomic absorption spectroscopy is an analytical technique used to determine how much concentration of metal atoms in solution. It measures the light absorbed by atomic absorption, and an atom changes from a ground state to an excited state by taking on energy from its surrounding in a process called absorption. This is an AAS in the actual laboratory setup. On the other hand, this is a diagram of atomic absorption spectroscopy wherein the sample is analyzed in the form of atoms. And these are the main components of atomic absorption spectroscopy. The first one is a hollow cathode lamp. A hollow cathode lamp is used as a radiation source in atomic absorption spectroscopy, and it helps in the excitation of ground state electrons. Also, it is enclosed in a glass envelope filled with the low pressure of an inert gas such as neon or argon. Second is a chopper. A chopper is a rotating wheel between a hollow cathode lamp and a flame. It removes large droplets and allows uniform-sized droplets to enter the flame. Also, it breaks the steady light from the lamp into pulsating light. This gives the pulsating current in the photocell that is amplified and recorded without any interference. Third is the atomizer. The purpose of the atomizer is to break up sample to free atoms by providing a high temperature. Atomizers consist of burners and flames. The fourth one is the monochromators. Monochromators are used to select the specific wavelength which is absorbed by the sample and exclude all other wavelengths. The most common types of monochromators are prisms and gratings. The fifth one is the detectors. Photomultiplier tubes are the most commonly used as detectors in AAS. These are used to convert electromagnetic waves into electric currents, and they are made up of photoemissive cathodes and diodes. These diodes provide electron multiplications. And lastly, the readout systems. The readout systems used in atomic absorption spectroscopy are meters, chart recorders, and digital display meters. These are the process in an atomic absorption spectrometer. When the radiation passes through the microwall and they are incident on a rotating chopper, producing intermittent radiations that are then directed at the excited atoms in the flame of a burner. These atoms absorb the radiations and then transmit the radiations reach a prism that is connected to a photomultiplier tube or PMT. The PMT produces current which is displayed on a readout meter that gives the absorbance, and by applying the Beer-Lambert's law, we can determine the concentration of the solution by knowing its absorbance. Moreover, atomic absorption spectroscopy is widely used for the analysis of trace metals in a variety sample matrices. It is also a versatile technique with a wide range of application in different fields such as biomedicine, lubrication, agriculture, food science, geology, environmental science, pharmaceuticals, and lastly, cosmetics. So let's move to atomic emission spectroscopy. So first, what is emission spectroscopy or AES? AES measures the intensity of light emitted by the excited atoms. The electron absorbs the energy and jumps to a higher energy level, and in the reverse process, emission, the electron returns to the ground state by releasing the extra energy it absorbed. So it is the AES in the laboratory setup, and it is the flowsheet diagram of AES. So these are the major components of atomic emission spectroscopy. So first is atomizers. Atomizers consist of flames and burners, and they're used for the conversion of solid or liquid samples to free gaseous atoms. Flame atomizers require oxidant or flame gases. Second is the monochromators. Prism and diffraction grating act as monochromators, selectively emitted radiation types and removing unwanted ones, providing better results and resolution than prisms. For this reason, it is sometimes called the wavelength selector. Third is the detectors. Photomultiplier tubes, photoemissive cells, or array directors act as detectors in atomic emission spectroscopy. They are used to convert optical signals into electrical current, which is then amplified by the amplifier. Lastly, the readout devices. Computers are used as readout devices in atomic emission spectroscopy. Computers analyze the data in the form of spectra and plot into the calibration curve using the atomic emission ranges library. AES has several quantitative applications including biomedicine, lubrication, agriculture, multi-elemental analysis, petrology, environmental science, pharmaceuticals, and lastly, nutritional analysis. And this is the process of atomic emission spectrometer. The process starts by injecting the aerosolized sample with the heat energy using flame, when the sample contains atoms that will take up this energy and jump to higher energy levels. These energy levels are unique to each type of atom and will result in different amounts of energy being absorbed. However, these atoms cannot remain at a higher energy level for a long time and will eventually return to the original level, emitting energy in the form of light photons during process. These emissions are known as atomic emissions. AES and AES differs in their operating principle, but these are the major differences. Atomic absorption deals with the absorption of light, whereas atomic emission spectroscopy deals with the emissions of light. Second is atomic absorption spectroscopy depends upon the number of ground state atoms, whereas atomic spectroscopy depends upon a number of excited atoms. The third one is in atomic absorption, the spectroscopy electron moves from the ground state to the excited state, whereas in atomic emission, the spectroscopy electron moves from the excited to the ground state. So question, how does an atom in a ground state becomes excited? Electrons get excited due to the absorption of energy in the form of heat or light. This process is known as absorption, and it causes the atom to change from a ground state to an excited state. The electron absorbs the energy and moves to a higher energy level. In the process of emissions, the electron returns to the ground state by releasing the extra energy it absorbed.
Second to spectroscopic methods of analysis is UV-Vis. UV-Vis spectroscopy is an analytical technique that measures the amount of discrete wavelengths of UV or visible light that absorb or transmitted through a sample, and it is used to obtain the absorbance spectra of a compound in a solution or as a solid. The main components of the instrumentation used are as follows. First is the light source, second is the lens, third is the grating, fourth is the wavelength selector, fifth is the sample, and sixth is the detector. First, the light source. Light sources that lie in the ultraviolet and visible region are used as a UV visible spectrometer sources. There is a several type of light source. First is the hydrogen or deuterium lamps that range to 160 and 380 nanometers in electromagnetic spectrum. Second is the xenon arc lamps, which range to 150 to 600 nanometers. And lastly is the tungsten halogen lamps, which range from 240 to 2500 nanometers. Second to the components of UV-Vis is monochromator. A monochromator is an optical device that is used to select a narrow band of wavelength of light, and it may be a quartz, prism, or grating. All monochromators are similar in mechanical construction, and the essential components of this are slit, mirror, lens, grating, or prism. Next is the sample container or cells or cuvettes. Sample containers or cuvettes may be made up of quartz, borosilicate, or plastic, but only quartz is transparent in both UV and visible regions. Glass and plastic are suitable for the visible region only, and glass is not suitable for the UV region because it absorbs UV radiation. Plastic cells are not used also for organic solvents. And lastly, with the components of UV-Vis is the detector. Detectors and radar are crucial components which is responsible for measuring the intensity of light at different wavelengths after it has interacted with the sun. Some examples of simple detectors are transducers or photodetectors. There are two types of UV-Vis. First is the single beam UV spectrometer. Second is the double beam UV-Vis spectrometer. Let's talk about first the single beam UV-Vis spectrometer. Single beam UV-Vis spectrometer has a single beam as the name indicates. The incident light coming from the source is passed through a monochromator, then that incident monochromator light moves through a slit, then it passes through the sample solution, where some of the incident light is absorbed by the sample, while other is transmitted. The transmitted light is detected by the detector, and the detected light is then amplified, recorded, and then displayed on a suitable readout device. Spectrum is plotted, and the lambda max is located. And here are the components of single beam UV-Vis: the light source, lens, gratings, wavelength selector, sample container or cuvettes, then the detector, and the digital bit or the recorder. Second, with the type of UV-Vis is the double beam UV-Vis spectrometer. It is when the light from the source, after passing through a monochromator, is split into two separate beams, one for the sample and the other for the reference. A double beam UV-Vis spectrometer needs two detectors that detect electron ratio to measure or calculate absorbance in a test sample, and it is also required to stabilize voltage supply. Listed here are the applications of UV-Vis. UV-Vis spectroscopy is used to identify organic and inorganic species that is present in a solution. It is also used to find the concentration of the unknown solution and for the determination or structure along with the other data such as bands and intensities of functional groups. It is also used in the study of chemical kinetics. And lastly, UV-Vis spectroscopy is also used to study isomers. UV absorption spectroscopy can be used for the quantitative determination of compounds that absorb UV radiation. This determination is based on Lambert-Bird's law that is used to determine the transmittance and absorbance of solution in a transparent cell with a path length. According to this law, the concentration of the absorbing analyte is directly proportional to the absorbance and path length of the cell. Beer-Lambert's law is based on two different laws. The Beer-Lambert law states that when a monochromator light passes through a transparent medium, the intensity of transmitted light decreases exponentially as the thickness of the absorbing material increases. While Beer's law states that the intensity of transmitted monochromatic light decreases exponentially as the concentration of the absorbing substance increases. Beer's law states that the intensity of transmitted monochromatic light decreases exponentially as the concentration of the absorbing substance increases. This Beer-Lambert's law can be expressed mathematically by the formula, where A refers to the absorbance. Here is the incident light and the transmitted light. Next is the molar absorptivity, and the concentration, and the path length. Actually, you can get both the reading of absorbance and transmittance in this formula. Let's have a Beer's law problem solving. As it said earlier, it can be used for chemical analysis that one can ascertain a substance's concentration in a solution by just observing the absorption of light at a particular wavelength. Analytical methods like UV-Vis spectroscopy use the Beer-Lambert law to calculate the concentration of the substance in a solution. Let's try to answer this problem. A sample has a molar absorptivity of 500 molar reciprocal and centimeter reciprocal, and a spectrophotometer measures absorbance of 0.75 using a cuvette that is 1 centimeter wide. Then find the solution concentration. To answer this problem, let's write the formula of Beer's law, then rearrange the equation and solve for the concentration. Then write down what you know, wherein absorbance is equals to 0.75 and the molar absorptivity of 500 molar reciprocal times centimeter reciprocal, having a path length of 1 centimeter of a cuvette. And finally, plug in the values and then obtain the answer. wherein concentration is equals to 0.75 over 500 polar reciprocal times centimeter reciprocal times 1 centimeter. And we can obtain the answer, which is 0.0015 mole per liters. Moving on with the infrared spectroscopy, or also called IR spectroscopy or vibrational spectroscopy. It is the analysis of infrared light that interacts with matter in the infrared region of the electromagnetic spectrum. An infrared spectrometer is an instrument based on absorption in the infrared region due to changes in vibrational energy. The IR region ranges from 700 to 1000 nanometers. Here are the components of infrared spectroscopy. First is the IR source, or the light source. Second is the monochromatic system with the splitter. Third is the sample cell, or reference cell. And lastly, with the detectors and recorder. Moving on with the components of infrared spectroscopy is the light source, wherein the radiation source should emit steady, intense, and extended IR electromagnetic radiation within the desired wavelength range. Therefore, radiation sources such as Nernst global source, incandescent lamp, and mercury arc lamp are used. Second, with the components of infrared spectroscopy is the monochromators. It is when the sample absorbs only certain frequencies of IR radiation, so we use prism and grating monochromators to select a desired frequencies. IR spectroscopy is used to analyze solid, liquid, and gas samples, so material should be used is IR radiation transparent. And lastly, with the components of infrared spectroscopy is the detector. It helps to detect the transmitted IR radiation by the sample. The detector should be placed and designed in such a way that it can detect even a low frequency signal. For that reason, thermal detectors are widely used in IR spectrometry. There are also two types of infrared spectroscopy. First is the dispersive infrared spectrometers. Second is the Fourier transform infrared spectrometers, which is a well-known type of infrared spectroscopy. First, with the types of infrared spectroscopy is the dispersive infrared spectrometers. When it is used, a dispersive element such as prism or diffraction grating to separate infrared light into its component wavelengths. It has the components of entrance slit, collimating optics, dispersive element, and focusing optics and detector. It has an advantages of simplicity, moderate resolution, and good for routine analysis. Its disadvantages is limited resolution compared to other types. Second to the well-known type of infrared spectroscopy is the Fourier transform infrared spectroscopy. It is used in interferometry to measure the amplitude and phase of an interferogram from which a Fourier transform is applied to obtain the spectrum. Its components is interferometer, beam splitter, moving mirror, detector, and the computer. It has an advantages of high sensitivity, high resolution, and rapid data acquisition. But it also has a disadvantages of more complex than dispersive instruments. IR spectroscopy is a widely used analytical technique in a variety of fields, including chemistry, material science, and biochemistry. Moreover, it is applied as follows. First is the identification of functional groups and structure elicitation. Second is the identification of synthesis. Third is the studying reaction pancreas. Fourth is the detection of impurities. And lastly, with the quantitative analysis.
The third topic under the spectroscopic methods of analysis part 2 is the molecular photoluminescence spectroscopy. Molecules absorb electromagnetic radiation which causes electric excitation. Then once it relaxes back to its ground state, photons are emitted and this process is called photoluminescence. Photoluminescence has two different processes which are molecular fluorescence and phosphorescence. For fluorescence, the decay of the molecule is from the singlet excited state to a singlet ground state, from which an electron returns to the ground state with a similar spin orientation. Meanwhile, an electron spin of a triplet excited state to a singlet ground state is observed for phosphorescence, and electrons returns to ground state with a different spin orientation. Fluorescence has a short-lived emission, or in other words, it decays rapidly. On the other hand, phosphorescence is long-lasting as it may continue for some time after removing radiation source. Comparing the lifetime of the electrons in the of comparing the lifetime of electrons in the excited state, phosphorescence is longer as it ranges from 10 raised to negative 4 to 10 raised to 4 seconds. Moreover, fluorescence are commonly observed from molecules with pi to pi star transition state and sometimes detected from molecules exhibiting n to pi star transition. And for phosphorescence, it commonly occurs from n to pi star transition. Furthermore, molecular fluorescence has two important mechanisms of relaxation. These are the non-radiative relaxation or radiationless emission that does not involve photon emission, and fluorescence emission where photon is emitted. To understand further, we have here a Jablonski energy diagram, which represents the energy of a photoluminescent molecule, displaying ground electronic state indicated by S sub 0 and many excited state indicated by these bold lines S sub 1, S sub 2, S sub 3, and so on. Between the states are different vibrational energy levels, which will help us distinguish various methods of non-radiative relaxation. This upward arrow is indicative of the absorption. So the first method of non-radiative relaxation is vibrational relaxation, wherein vibrational energy level changes but within the same electronic state of energy only. Yeah. It happens when excited molecules collide with molecules of solvents. It occurs more rapidly than fluorescence. The second one is internal conversion, where it is a relaxation from the lower vibrational level excited state, or for this example, from S1 to higher vibrational level of another electronic state, the V sub 5 of the ground state. Next is external conversion, where external energy is transferred to the sample or another matrix component. Then the last one would be the intersystem crossing. It happens when electronic spin state differs and a change from the singlet to triplet state occurs. So this relaxation is commonly observed to heavy atoms such as bromine and iodine. Fluorescence emission is depicted by the downward orange arrows, wherein molecules relax from the lowest vibrational level of an excited state to different vibrational levels of ground state. And it produces bands of radiation, which the wavelength of the photon emitted is different from that of the wavelength that initially caused its excitation. That is why it is called fluorescence. Lastly, the pink arrow represents phosphorescence, which a relaxation from the triplet excited state to the singlet ground state accompanied by emission of photons takes place. Let's try answering this problem. Um, what type of relaxation are present in the given Jablonski diagram? You can try to pause the video to answer. So three methods of relaxation are displayed in this diagram. So the answers are vibrational relaxation, which is this one because it changes vibrational level, but it is within the same electronic state. The next one would be the internal conversion. It's a change from the lower vibrational level of the S3 to the higher vibrational level of the S2. Then lastly, this one is the fluorescent, represents fluorescence because it's from the excited state to different the vibrational level of the ground state. So how can we determine the efficiency of fluorescence or phosphorescence? it can be explained by the concept of quantum yield and intensity. So in molecular fluorescence, the quantum yield is the ratio of number of photons emitted to the number of photons absorbed. Or in simple terms, it is the measure of the probability of the molecule to fluoresce. So when it is equal to 1, fluorescence occurs. And it can even approach unity for highly fluorescent molecules like fluorescein. In contrast, non-fluorescent species has a quantum yield equals to 0. And there are different factors that affect quantum yield, such as the electron withdrawing group. So an increase in EWG decreases the quantum yield. For electron donating groups, they are directly proportional with the quantum yield. The next one is temperature. So as temperature increases, the deactivation by external conversion um, has a higher chance to occur because of increased collision between molecules, thus lowering the quantum yield. For solvents, so low viscosity solvents is also affected by a higher chance to undergo the activation by external conversion. That's why their quantum yield also decreases. Aromatic rings, compounds with simple heterocyclic aromatic rings does not fluoresce, but fluorescence or the quantum yield increases as the number of rings and degree of condensation increases. Then the last one is structural rigidity. So uh, it favors structures that are rigid as the rate of the non-radiative relaxation are being lowered and thus fluorescent emission takes place. So the intensity of fluorescence is given by this equation, wherein when the absorbance is less than 0.05, the equation can be expressed as this. So we can see the linear relationship between the intensity of fluorescence and the constant for efficiency of fluorescent emission, the quantum field, incident power of the excitation source, concentration of fluorescent species, path length, and molar absorptivity. For phosphorescence, its quantum yield is improved by decreasing the external conversion efficiency. And its intensity of phosphorescence is similar from that of the intensity of fluorescence. Let us try to answer another sample problem. So, which of the following among the sets has a higher quantum yield? For letter A, is it this structure or this? So, for letter A, the 8-hydroxy quinoline with zinc complex has a higher quantum yield because of its rigid structure as compared to only this 8-hydroxy quinoline structure. Remember that structural rigidity is directly proportional to quantum yield. Meanwhile, for letter B, since the structure in the lane has more rings as compared to this, therefore it has a higher quantum yield. This spiral structure is heterocyclic and does not exhibit fluorescent properties. After discussing the concepts and principles behind fluorescence and phosphorescence, let us try to understand further how they work as an instrument. The components of molecular fluorescence involve excitation source, which are typically mercury arc lamps, xenon arc lamps, the combination of the first two, or laser. So from the source, it passes through a wavelength selector towards the sample, where from which the radiation is absorbed by the sample. Then the sample emits light that will pass through an emission wavelength selector to a detector, and signal is processed using a computer. As you can observe, there is a 90 degrees, the detector is 90 degrees from the optical path, which is designed to avoid light interferences from this excitation source. Moreover, when both wavelength selectors are monochromators, so the instrument is called spectrofluorometers, while if filters are used for both these wavelength selectors, then it is called fluorometry. Moving to the sample cells, so fluorescent analyte are measured using a fiber optic probe, while an addition of fluorescent probe is utilized for non-fluorescent analytes. What differs phosphorescence instrumentation to the fluorescence is the two choppers that are positioned with the sample in between them. This is to delay the process of absorbing and emitting light to prevent fluorescence emission and rather produce phosphorescence. Lastly, phosphorescence is slow process. Thus, excited state should be prevented to relax by external conversion. Some of the ways to minimize it are dissolving samples in solvents, which includes ethanol, isopentane, and diethyl ether, or freezing the solid matrix. Then immobilize sample in solid substrate. The next topic, moving on to the next topic, have you ever wondered why sky is blue and why does it turn orange during sunrise or sunset? This is due to the phenomenon of light scattering of particles in the atmosphere. So, scattering can be divided into two. We have the elastic scattering and inelastic scattering. So, for elastic scattering, energy of radiation that is absorbed and re-emitted by the analyte remains unchanged. That's why it's elastic. So, in elastic scattering, there is an observed change in energy of the radiation absorbed and re-emitted by the analyte. Elastic scattering can be further classified into two. So we have Rayleigh or small particle scattering, which the scattering particle's largest dimension is less than 5% of the radiation's wavelength. The second one is large particle scattering, wherein the distribution of scattered light increases in forward direction and decreases in the backward direction as affected by these destructive and constructive interferences. There are also two techniques for measuring scattered light. The first one is turbidimetry. So the light source is linear to the detector, and the intensity of light transmitted through the sample is measured. So wavelength selection is necessary to avoid other radiation that may interfere and absorbed by the sample. Moreover, turbidimetry is suitable for samples that have high concentrations. So one way to measure turbidity is using transmittance, which is the ratio of the transmitted intensity of radiation source, or IT, to the transmitted intensity of the lamp. The relationship of transmittance and concentration is given by this equation, which is similar to absorbance. The second technique is nephelometry, which is the measurement is done at an angle of 90 degrees from the light source. So the size of these scattering particles is small, that Rayleigh scattering can be seen. So as compared to turbidimetry, which are suitable for high concentration, nephelometry is for low concentration that has few the analyze has few scattering particles. So the concentration for the nephelometry can be determined by using this equation, wherein the intensity of scattered radiation is equal to the constant obtained from standard calibration curve multiplied by the intensity of the incident source of radiation times the concentration of scattering particles reported or expressed as weight by volume. How can samples for turbidimetry and nephelometry can be prepared? So, scattering particles are prepared by precipitation. So, in maintaining the particle size of samples and standards, the parameters that can be controlled include the following. So, we have the pH, the concentration of reagents, the order of adding reagents, temperature, agitation, ionic strength, and the time of formation of precipitate and measurement of the scattered light. So surface active agents stabilize the precipitate in colloidal state. So examples of these agents include dextrine, gelatin, and glycerol. So the applications of turbidimetry and nephelometry includes the determination of suspended materials in water, sulfur in organic materials, amylase activity using storage of substrates, and of course, once again, water testing. The